Okay, our discussion is on simple stress. So basically, simple stress are expressed as the ratio of the applied force divided by the resisting area. So if we try to express it as mathematically, you have your simple stress or stress sigma is equal to force all over area. So it is the expression of force per unit area to structural members that are subjected to external forces and or induced forces. So stress is the lead to accurately describe predict the elastic deformation of a body. So simple stress actually is categorized or classified into three. It can either be a normal stress, a shear stress, and a bearing stress. So let's talk about first normal stress. So when you talk about normal stress, it develops when a force is applied perpendicular to the cross-sectional area of the material. So if the force is going to pull the material, the stress is said to be tensile stress, and compressive stress develops when the material is being compressed by two opposing forces. So stress is the expression of a force applied to a unit area of surface. It is measured in PSI, in English unit, or in megapascal for SI unit. So another unit for stress which is not commonly used is the dyne. Stress is the ratio of force over area. So for this one, for the normal stress, of course, we have our equation. As mentioned, this is a resisting area. The resisting area is perpendicular to the applied force, thus normal. So the formula that you will be using is normal stress is equal to P all over A. So our P is the applied normal load, which is in Newton, and A is the area in mm squared or millimeter squared. The maximum stress in tension or compression occurs over a section normal to the load. So if you're going to have this bar, this material, and if you apply a pull on the material, so you have a tensile stress. So the bar is in tension. However, if you are applied a compressive force, so you have a compressive force, so the bar is in compression. So in tension, the bar is in tension. If you apply this force, you apply a force, a pulling force. So this is the applied force, our P. And for this one, this is the bar is in compression if you applied a compression force. So it pushes, the force at both ends pushes the material. So you have here our applied P. So you have your bar in tension and you have bar in compression. Okay, let's have problem number 1. A hollow steel tube with an inside diameter of 100 mm must carry a tensile load of 400 kN. Determine the outside diameter of the tube if the stress is limited to 120 meganewton per meter squared. So we are given here with a figure. So this is a hollow steel tube which has an inside diameter of 100 mm, and you have here the hollow steel tube carries a tensile load equivalent to 400 kilonewton. So we are asked to determine the outside diameter. So this is our outside diameter denoted by D. So what will be the value for D if the stress is limited to 120 meganewton meter squared? Okay, for our solution, Of course, we make use of the formula stress is equal to P all over A. So we have stress which is equal to the force all over the area. We have to take note that our P, based on our given problem, is equivalent to 400 kilonewton, or this is actually equivalent to 400,000 Newton. And for our area, so basically for the area, that will be equivalent to, in terms of diameter, we will be using the formula pi d squared all over 4. So this is the formula that we will be using, pi d squared all over 4. Since we have an inside and outside diameter, we are required to compute for the outside diameter. So basically, our area would be equivalent to pi d squared all over 4. This is our outside diameter subtracted by our inside diameter, which is pi d squared. Our diameter, inside diameter, is equivalent to 100 raised to the second all over 4. So if we try to have this equation, we can have pi all over 4 quantity d squared minus 10,000. So we are required to compute for our outside diameter denoted by d. So therefore, from our equation, which is sigma stress all over P all over A, so we can have our P equal to stress times the area. So if we try to substitute the value for each variable, we will have 400,000 equal to 120. This is the limiting stress that is given on the problem. Then multiplied to the area, which is equivalent to this expression, which is pi all over 4 times d squared minus 10,000. And if we try to simplify further, we can have this expression 400,000 equal to 30 pi d squared minus 300,000 times pi. And since you are after for our d, try to manipulate the equation so we can have d squared is equal to 400,000 plus 300,000 pi all over 30 pi. So of course this is only transposition. So if we try to transpose this expression, if we try to transpose this expression, so that will be negative. This 30 pi d squared transposed to the left, so that becomes negative. This one 400,000 transposed to the right, so that becomes negative. And of course, this is negative 300,000 pi, multiplying both sides by negative, so we came up with this expression. And if we try to get the square root of this, we'll try to simplify. Our d is equal now to 119.35 mm. So this is now the unknown outside diameter for our given problem. Okay, let's have problem number 2. A homogeneous 800 kilogram bar AB is supported at either end by a cable as shown in the figure. Calculate the smallest area of each cable if the stress is not to exceed 90 megapascal in bronze and 120 megapascal in steel. So we are given with our figure. You have the two cable for the bronze, which is having a length of 4 meters, and for the steel you have a length of 3 meters. These are the support for our homogeneous 800 kilogram bar, which so if we try to of course the homogeneous 800 kilogram bar AB has a length of 10 meters. So for our solution, so we start first for let's try to have the free body diagram. So if we try to draw the free body diagram, we have to identify the forces that are acting, which are, we have the force exerted on the cable for the bruise. So we denote this as P sub B. And we have the force exerted on the steel. So we denote this as our piece of ST. So we can have here piece of BR. And of course, we have the weight of the bar, which is equivalent to 800 kilogram, or multiply this so that you can have the length 9 times 9.81. So we get the value of 7,848 Newton. Since we have now our free body diagram, our unknown here is to calculate the smallest area of each cable. So what will be the smallest area for our cable? For cable on the bruise, cable on the steel. So for that one, if we try to identify the forces first, we try to identify the forces on the cable, our PBR and PST. Of course, they are symmetrical, so we can have the equation that the force on the bronze cable is equal to the bronze on the steel cable. So this is equivalent to, so since this is summation of forces vertical, so actually we can have the equations summation of forces vertical is equal to 0. So we can have the equation that PBR plus PST is equal to 7848. And since PBR is equal to PST, so we can have the equation that 2 PBR is equal to 7848. And from here, we can have the force, which is equivalent to 3,924 Newton. So we have now our forces. So for the area of the bronze cable, let's start for the bronze cable. So basically from the equation, P force is equal to stress times area. So we have 3924 is equal to the limiting stress on the bronze is equivalent to 90. So we have 90 times A. So area on the bronze is equal now to 43.6 mm squared. And for the steel cable, we have force on the steel is equal to stress times area. So this is 3,924, which is equivalent to the limiting stress on the steel is 120 multiplied to the area. So therefore the area on the steel is equal to 32.7 mm squared. So the area on the two cable for the bronze is 43.6, and for the steel the area is 32.7 mm squared.